Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Let's get started for day 2. And this morning, my name is Masato Shoichi, and I'm going to chair the morning session. The first half, we have 2 keynote talks. The first speaker is James Crutchfield on the Macroscope, the engine for pattern discovery. James.
Great. Thank you. Well, you're not my usual audience. But then in talking to people yesterday, listening to discussions, I realized maybe we're not our usual audience. Kind of a motley crew trying to figure out what you're doing and who you are and if there's something here. So with that in mind, what I'd like to do is paint a certain kind of picture, doing this a bit in a historical perspective of my own interest and study of very complex, large-scale systems. One of the themes is to try to emphasize or maybe plead or beg for the role of theory as an important component in doing computing and gathering large data sets. I've actually become a little bit concerned about the role of theory. I do have a positive message I hope that I'll be able to convey. Of course, not in such a short talk. There's many things I'll be sort of skipping over. And since it is a short talk, let me just give you the executive summary. So the talk is going to oscillate between being provocative and obvious, between the sublime theory and mundane gadgets. And I like sort of oscillating between all of those extremes. So for me, big data is not enough, nor is building larger and larger machines. I have spent my entire career building instruments that help me understand how nature organizes itself, how randomness is produced in the natural world. And I'm going to try to give a little historical summary of why that's sort of necessary and the fundamental role of computing. And I'm going to come back and talk a little bit about, in that context, the role of theory and maybe try to flatter the astrophysicists here by pointing out the long, long history that astronomy has had in pushing some even more abstract ideas I'm going to talk about. The optimistic message, the kind of conclusion I've come to, although, like I say, it's sort of a vision thing, is the possibility of actually automating science. And I mean that in a very particular context. When we have very complex, large-scale systems, how is it that we discover something new? So in the talk title, I use the phrase pattern discovery, and I want to make a distinction between what's probably more familiar, pattern recognition. When you call up American Airlines and you say Chicago, you're talking to a machine that some poor speech engineer has spent literally months, I have a friend that does this, tweaking hidden Markov models to recognize the particular frequency response in small time windows. Pattern recognition in that sense, successful engineering technology, it requires a built-in vocabulary, a set of templates against which our little digital signal processors compare, and the one that's closest becomes Chicago to the machine. That's not what I want to talk about. We do this all the time. It's very successful. When I say pattern discovery, I want to know where the vocabulary came from in the first place. What is the set of templates? The positive message is that over the last century, we have a number of techniques that let us actually think about this issue and frame it, I think, in a precise way. So if you're interested in some of the theoretical aspects, there's just this last January, this year, I have a review in Nature Physics. So please go take a look at that and give some of the background going back to the origins of the theory of computation, celestial mechanics, dynamical systems, nonlinear physics, and tries to weave these things together to make this case more plausible. OK. So this will be the sublime. I'm going to end with the things that kind of entertain me when I don't want to take another derivative, namely gadgets. I want to talk about tools that help accentuate, that I argue will accelerate discovering new patterns. Okay, a little bit of history. This is maybe revealing myself, kind of dating things here. How many people know what this is? Any guess?
Analog computer.
Congratulations. In particular, it is a Systron Donner SD1020. This machine is near and dear to my heart. What do analog computers do? They solve differential equations. So why would I care about an analog computer? Well, in the 70s, I was very interested in various kinds of very nonlinear equations for which you could actually show some of the mathematics I've alluded to. You can't write down a closed-form solution. Therefore, you have to simulate. And hence, the beginning of this long sort of focus on tool building in the service, for me, of building theory and trying to understand how systems are organized, but computing, simulation. This particular one, although it was actually built in probably the late 60s, you can't really buy these things anymore. It makes me greatly sad. You have different modules here, operational amplifiers, multipliers, and we're showing it in the unprogrammed state. And you patch all these things together. It is a parallel computer. All the modules operate simultaneously. And it runs extremely fast. And probably in this size of machine, you could probably do, say a set of 20 first-order differential equations, probably running anywhere from, well, as slow as you like. You put in different capacitors, anywhere from a few cycles per second in the natural frequency up to maybe 10, 20 kilohertz. At the time, when I was using this in the late 70s, that obviously beat the pants off the PDP-11 I was using by a long way. And in fact, I would still kind of argue, not so much for the speed, but because a very important interface decision engineers made: knobs. It seems like a trivial point, but there's something about looking at the solutions as they change as you twiddle the knob, because there is an interactive feedback loop that is very short and intuitive. And I'm going to come back to this. In some sense, I've been trying to, through this long digital distraction since the 70s, get back to a system that is as natural for discovery as an analog computer is. Of course, in a digital setting, I can do more sophisticated things, larger systems, and so on. But it's a little bit kind of a sort of irony in terms of, shall we say, GUIs. Is that a GUI? It's an instrument panel, damn it. And of course, people doing music synthesis and VJs and so on have, interactive interfaces like this, sliders and so on, trying to fake the naturalness of this sort of thing. Okay, so that's just, I'm kind of grounding myself here. You got to know a little bit where I'm coming from, this old analog world, and my heart still pines every once in a while for this, especially when my code doesn't compile. So I want to argue now in terms of fundamentals why we must compute. Maybe yesterday, and maybe kind of the context of the workshop, it's a little bit, systems are big, we have big data sets, we have big machines, big systems of equations we want to solve. I actually want to argue that even for small but nonlinear systems, we have to compute. And this is based on a good deal of mathematics developed in the late 19th century, but mostly through the 20th century. First point, nature spontaneously organizes. There are emergent structures in the world. And what do I mean by that? Well, this word emergent is now getting heavily abused, but it means something very, very immediate and practical, that the structures and patterns produced by the system are not directly specified, not directly derivable from the equations of motion. If you write down a differential equation, sure, you can put the left-hand side to 0 and find the fixed points. Or maybe it could be computationally difficult, but you've reduced it to computational quadrature. I'm talking about systems where, over long spatial scales and long times, structures emerge that, again, are not given by the equations of motion. And there are just way too many examples to go through. Fluid flows here. It's von Karman vortex street. Baynard convections, fluid, thin layer of fluid heated from below. Same thing here, convective cells in this hexagonal, these little donuts. These are two immiscible fluids under high pressure. Belousov-Zhabotinsky reaction. You're looking down on a petri dish with 5 reagents. They actually spontaneously start to oscillate in every little fluid volume, and then those oscillations get synchronized, and we recognize these as traveling waves of reactions. Unpublished for about 10 years because at the time in the late 40s and early 50s, when Belousov and Zhabotinsky did the experiments, this was thought A, to be impossible, so that's the first round of rejections. B, uninteresting because it's transient. And finally, they got it published. This became one of the paradigms for understanding how order spontaneously arises in nature, the Belousov-Zhabotinsky reaction through reaction, diffusion, partial differential equations. But pattern formation occurs in the natural world. This is a petri dish, bacteria. The evil biologist put some toluene here, and the bacteria actually get together and kind of race away from together in these patterns. Zebra striping, animal striping is also described by a very similar sort of reaction diffusion system. Butterfly wing patterns, and it goes on. This looks like a micrograph of the vascular system of a leaf, but in fact, it is what happens when you take a piece of plastic and you stress it and it cracks. The point is, nature spontaneously organizes, and one of the goals of science is to understand what these patterns are. It's almost like different fields are sort of defined by what we decide to attend to. Right? So, hidden in this is actually the mathematics that's developed, maybe even in this case, kind of the last half of the 20th century. We actually understand a lot about the mechanisms in the system state spaces that lead to these different classes of pattern. And so in some sense, there is a kind of predictive theory behind many of these systems. Sometimes the analysis is quite hard. I'm not claiming we can do every one of these things, although BZ's done pretty well, but Vortex Street's done pretty well, so on. Not only natural systems, right? As the intelligent little beings that we are seem to be hell-bent on building gigantic social technical systems now. And, just like before, there are consequences of building these large social technical systems that we don't understand. Just one example, internet route flapping. I don't know if anybody remembers this from the early 90s. So if you went to the catalog from Cisco, well, actually, it wasn't a very big catalog back in the early 90s. It's a small company. And you paid your $65,000 for a router, and you guaranteed 100,000 packets per second throughput. As soon as you deployed these things and put them out on the network, what happened? Suddenly, in fact, this was noticed across the entire network in the early 90s, throughput would start oscillating on time scales of seconds to several minutes. Huh. You know, you made a bad purchase, right? You looked at the spec sheet and you said 100,000 packets per second. You weren't getting it. Sometimes you were getting 0. What the hell is going on? Well, it turned out that the engineers designed the protocols, the control protocols, in isolation. In fact, the control protocols, to simplify a rather complicated story, they tried to be smart. They tried to add smarts. Oh, I have a map of my connections. Oh, there's a lot of traffic over here. The router, I'm going to switch to everything, putting my packets over this way. Well, what happens if everybody decides that? You know, low traffic, high traffic, low traffic, high traffic. And then this propagated. That's just one example. I mean, obviously, this is maybe more immediate concern to us now. We build regulatory systems and have notions of philosophical pictures of how an economy is supposed to work and what good business practices are. Nonetheless, these systems can fail right in front of us, even in a system with the best of intentions. Forget fraud. And so on. So, power grid failures, India, right? What was there? A third of the country goes down, no power for hours and hours and hours. Wonder what happened. So this notion of emergent structure, it's important, not only as kind of a natural scientist looking out at the world, realizing that when you write down the equations of motion, the model, that doesn't tell you everything, and also the systems we build. So I see this as a very broad set of problems. Okay, but the consequence, at least from my argument here, is that because of this, these things, the emergent structures are not directly determined by the equations. Basically, every system needs its own sort of function basis, its own explanatory basis. And then the issue for me, for pattern discovery, the way I frame pattern discovery even comes up, is that we don't know this ahead of time. There's some process that obviously we seem to be pretty good at as, say, natural scientists, at sort of figuring out how the systems are organized. I'm interested in studying that process of discovery well enough that I could teach a machine to do it. So that's a tall order. The mathematics gives me some sort of optimism. So, why do we use computing in this setting? Just to explore what's possible. There's a lot of kind of exploratory phenomenological work and just looking at different kinds of nonlinear equations, seeing how they can behave. A large part of this area dynamical systems theory is based on coming up with classifications of nonlinear behaviors that actually don't require solving any differential equations. Uses geometry and topology and so on. Okay, so nature forms patterns. First reason we want to compute is to explore just what's possible, just to give us some intuitive sense of what's possible out in the world or in the designed world. Another reason to compute, and so here, let me go back to the early days. So this is Laplace in late 1700s talking about, actually these quotes here are from the preface to his book on probability theory. So first he starts off, of course, setting the context of trying to explain why you need probability. Well, so the first thing is to set up the kind of straw man, determinism. And we all know this quote, right? If we conceive of an intelligence which at any given instant comprehends all of the relations of the entities of this universe, it could state the respective positions, motions, and general affects of all these entities at any time in the past or future. Nice, clean statement of determinism, reductionism there. Just to remind you of the role that astronomy has played. He goes on, physical astronomy, the branch of knowledge which does the greatest honor to the human mind. Gives us an idea, albeit imperfect, of what such an intelligence could be. So, of course, you go back, the French analysts, 1617, amazing. I've been studying some of the history. Just amazing calculational apparatus developed to deal with planetary motion, really. Okay, punchline, right? He's writing a book on probability theory. So here's his theory of why you need notions of chance. It's due to ignorance. So it is that we owe to the weakness of the human mind one of the most delicate and ingenious of mathematical theories, the science of chance or probability. Because we can't be this omniscient, all-seeing, all-measuring supercomputer intelligence, because we fall short of that, the world will appear to us to be, to different degrees, probabilistic or random. Okay? That's it. It's just ignorance. But if, we could get to this ideal intelligence, then everything would be certain for us. Well, maybe some of you know the punchline to the story. Poincaré comes along, and I point out again the role of astronomy. In his book, New Methods of Celestial Mechanics, he's studying the three-body problem, a book written in a chagrined state because, in fact, he proved the stability of the three-body problem and won a prize given to him by the King of Sweden. 6 months later, the manuscript was going to press to be published, and the typesetter sent him a note saying, oh, I think there's a sign error here. He realized the entire proof was wrong, and then produced a 1,700-page book over the next year that shows that this deterministic chaos is absolutely fundamental. So it may happen that small differences in the initial conditions produce very great ones in the final phenomenon. A small error in the former will produce an enormous error in the latter. Prediction becomes impossible. And what he introduces in this, well, he didn't have computers back then, poor guy. Just hand calculation, coordinate transformation after coordinate transformation. I don't recommend reading the entire book. However, pick it up sometime and just look at the last chapter from where this comes from. He just kind of throws up his hands. I can't even draw. I'm not even going to draw for you the sort of delicate interweaving of these solution sets. Developed a picture that has persisted to this day, and actually many of the insights from this work laid the foundations for this kind of what we call qualitative dynamics, a structural analysis of how state space of these chaotic systems are organized. It's absolutely fundamental, even as in mechanical systems as simple as a sun, an Earth, and a massless moon, restricted to orbit in a plane. Fundamental, chaotic, this mechanism. Now, there are practical consequences for this that we are concerned about. So in the 20th century, we came to understand that if we have some kind of time series here, and what we would like to do is make some measurements, some early time, trying to characterize what the current state of the system is, and then we want to predict the state of the system later on. The time series are shown here are the three different coordinates x, y, z of the Lorentz differential equations. But sort of more generally, we know now when the system is chaotic, the accuracy in our prediction decays exponentially fast. Hence, we have to measure again because this current measurement gives us a certain amount of information about the state. We lose that exponentially fast. Or to turn this around, the amount of data we need to accumulate, either the accuracy that we have to employ at getting the state, how often we have to measure, that grows exponentially with the prediction horizon. Also, the amount of compute time. You have to use increasingly accurate arithmetic in your calculations. Even assuming you can handle these two other things, the compute time also explodes exponentially. As in, absolutely fundamental. There's no way around this. So, consequence of this, there are no shortcuts. As I mentioned before, actually you can prove, if you want to get sort of mathematical about it, there are no closed form solutions that give you from the initial state the state of a chaotic system in any arbitrary time in the future. Can't. No closed form. You can prove, you can't write down. Interesting kind of proof. You can't write down the solution. And no computational speedups. You basically, if you want to know what the state is, you've got to invest all those exponentially growing resources to actually calculate that trajectory. If you don't do that, if there's a little bit of error, the error is going to grow so large that after a finite time, your error is going to be as big as the entire set of solutions. You won't know where it is. So, okay, so this is kind of, this is what theory has told us about these large-scale, complex, nonlinear systems. And I see computing as a response. Why did I go to the analog computer and not the PDP-11? Because I just couldn't simulate the things fast enough. It turned out there was a level of hidden patterns in looking at the time series, which had to do with the topological structure and the geometric structure of the solution sets. And I wanted to see those shapes and patterns. To do that, I needed to study these systems interactively and see thousands and thousands and thousands of solution sets. And I like doing that by turning knobs, because I could see it on my oscilloscope screen. So emergent organization, unpredictability, and even we have too limited a view of the world around us, the wrong theories, and so on. So these fundamental problems, for me, beg the question of, how do I discover something new? I can't just do incrementally better, because of the exponential scalings you'll quickly reach. You double the time you need, 4 times the resources. So you have to do something else. It means you have to understand, in a fundamental way, how these systems are organized. And that, I think, is, or maybe I was reading into some of the comments yesterday about what the goal is of providing these astroinformatic tools. What are you trying to do? You didn't so much talk about it yesterday, but once you have all this stuff running, let's just imagine your wildest dreams, you're successful. You can store as much data as you want. You can compute as much as you want. It's redundant, copied all over the world. At the end of the day, you're still sitting in your office. All the stuff is laid out for you. What are you going to do with it? There's that next stage of discovery. And a little bit understanding how that process works should tell you how to design the tools too, right? Okay, so on the upside, I just gave you a proof of guaranteed employment for those of us who compute. So we can rest a little quietly satisfied for a little while anyway. Now, and maybe I was sort of hinting at this, the idea that we can just make bigger and bigger machines to make progress alone, just by building bigger machines or collecting bigger data sets, I think is just flawed. And I just gave you a sketch of the theoretical reasons for that. So, in particular, the more, it's a funny irony. The more powerful these machines are, they approach, in, say, the simulations they can do, the sophistication of the natural world. Right? You have some companion star dropping mass into the accretion disk, and you're doing it rock by rock, and great. And what did you understand? You may have questions you want to experiment with that simulation, but that doesn't lead to understanding. So in this, for me, I want to separate out sort of understanding and the role of theory from just building better tools. I think there's something else, and I think there's a way to appeal to some of the theory I alluded to show us how to do this. So we need sort of new tools for understanding. Yes, big data. Yes, big computing, but also big theory. So same kind of comments on just building bigger data sets. Complex systems these unpredictable systems require you to take huge amounts of data. It was a little bit odd in the early days of all this to have to argue with your program manager that I needed databases to study low-dimensional nonlinear systems because I wanted to store all the data they produce, the diversity of data. To do this qualitative topological geometric analysis that we did, I needed vast amounts of data. Okay, so moving away a little bit from sort of the provocative and critical part of this, I want to propose very quickly some kind of solutions, and we'll end up with some kind of hopefully bailing things out here with some toys. So the very presumptuous goal is to come up with a theory of theory building. What is that discovery process? Right? I want to study how we build models of the order, the kind of geometric structures, somewhere between the sort of Laplacian determinism, focusing on particular solutions, and the other extreme is just throwing up our hands and calling it all random. Right? All those pattern-forming systems I just showed you are neither of those two extremes. There's something about how they're organized, and we recognize it. Right? I used those two-dimensional visual patterns because we have this evolutionary inheritance of visual recognition. So the claim is that we should be focusing on direct computational support for theory building. And I really don't see much alternative to this. Eventually, right, after the genome was sequenced, finally the biologists came around and said, oh, there's a thing called systems biology, which has to do with how genes interact. Huh. Right? It's okay. So at some point, you're back sitting at your desk, you've got all the tools that current technology will let you put together, and you still have to sit there and think. So what set of tools do we need to help us understand that and see the patterns? Quick example of this. Here's a little universe. It has one dimension, 287 binary sites. The ends are neighbors, and I start off in some arbitrary bit pattern. There's a local deterministic rule. Each site looks at its two neighbors and its own bit value and makes a decision what it should come at the next time, and you get this complicated pattern. Let me not go through this in detail. It's called a cellular automaton. Initial state down to state at time 99. Hidden in this is actually these particle structures. There are regions of kind of homogeneous texture. There are boundaries between these things, and there are two different kinds of these things. So in that midst that I just showed you, exactly the same data, a little daemon here that knows about the background texture has been run over that same data, and it pulls out these particles. So how was that discovered, this sort of kind of hidden particle physics? Well, there was actually a huge computer-assisted proof system that we used that would go through, and I won't go into detail here, but doing a kind of exhaustive search of different candidate background textures, pruning these things off by counterexamples and so on, trying to decide whether the candidates were an expanding set in the state space, a contracting set, or the goal, these space-time shift invariant domains. The product was a table like this of basically about 1 million theorems. This isn't numerical computing. What it's returning is algebraic results. It's completely clean. No round off here. And actually showing that Rule 22 had these domains. So to kind of say this sort of most prosaically, you say to the system, I want to study elementary cellular automaton 110, particular set of interactions, or Rule 22. And it returns the domains. These are like vacuum states. It returns the particles. These are the excitations above the vacuum states and the particle interactions. It basically gives you the full, I don't know what you want to call it, artificial particle physics in a completely automated way. It discovers the emergent structures. So this particular case, granted, it's just binary world, but at least for me, it provides a proof of concept that you can have a completely automated discovery system. So what about these tools? So let me just go through this quickly and mostly just show you two quick films. So nature is complex. Our minds are limited, but how can we extend them to build new kinds of tools? It's a kind of cognitive ergonomics for science. Not only do I want to understand how the world can make organization and patterns, but I also have to understand what the human observer's limitations are. And that's where the engineering comes in, to help sort of match these things. I mean, there are people that study visual and acoustic psychophysics. These people should be talked to. It's sort of like a grand GUI design, if you like, but much more informed about the complex nature of the world. So one of the ways I've been looking at this is using, and some of you have seen these things since you've been around supercomputer centers, a cave environment. So I have 3 walls and a floor. Each surface is stereographic projection that you look at through LCD shuttered glasses, and then you have your silly sort of game analog, so-called wand. Actually, the most important part about this, beyond what you'd see at your 3D theater, is this little bar up here. The system tracks the location of your head and where you're looking. And this point I want to make is impossible to make. You can't understand the importance of controlling software by just moving around through it until you do it. It's one of those things. So here's just a simple example. This is Oliver Krylos. He's the chief software engineer for the software system underneath all of this. He's actually designing a protein here interactively. There are different views he's got. He's grabbed onto a little beta sheet and manipulating that around. There are different views of the same structure, the sort of atomic composition, rather than the abstraction of alpha and beta sheets, alpha helices and beta sheets, and so on. I'm using this to study and teach mathematics of these chaotic systems. Of course, I torture my students endlessly at the blackboard, making them sort of work through the abstractions, and then at the end of the quarter, we go into the cave. And within minutes, they get these things. I was trying to, how do these different surfaces interact here? So what you're looking at is a tool that is, think of the analog computer, finely recapitulated, a differential equation solver. And what Jordan, one of the programmers, is doing, he's actually changing in real time the parameters, the coefficients in the equations, looking at the solution sets. There are different ways we can look at this to see how these complicated solution sets, in this case, the Lorenz attractor sheets sort of suture together. There are many other ways of probing these differential equations. Here we're showing you one solution set in gold, that's one particular solution, and 150,000 other initial conditions evolving. And as the system is solving this, you get to walk through it and stick your head inside of it. Within seconds, you can figure out the geometry, which is the goal. That is how these solution sets are structured. That's what I needed to understand way back when I was studying these things on the analog computer. A little criticism here. The control interfaces here, these things, they're menus. This is like importing all the debates we had back at Xerox PARC about how people should interface through GUIs. That's terrible. One of the most interesting things about this domain, having a cave like this immersive environment, is the new kinds of interface that are possible. And we haven't even scratched the surface. To import all of these motif-like widgets, it's a disaster. It's so completely unnatural. There have to be other ways. And just like at Xerox PARC, the debates we had in the 70s and 80s about what fiction should we present to the user so these bitmap displays and the hard disk, the state of these things made sense. Now we have the desktops. We all take it for granted. We're in exactly the same position now with these 3D devices. So that cave is a $500,000 single-user device. Kind of prohibitive, but we've made some progress. We've now lowered the point down to 5K, and here it is. So this is the current instantiation of the Macroscope. Your favorite Samsung, Sony 3D TV, plugged into your Unix box. We have 2 GPUs in there, one for the graphics display running OpenGL, and the other for doing the HPC simulations. In some ways, almost more importantly, we have this thing. This is a game controller that you can move in 3 dimensions called the Hydra Razor, $100, and it gives you X, Y, and Z, and you have a knob joystick and then buttons on the end of it to interact with it. You can't quite tell, but there's a little control knob here, and I'm actually pulling out this sphere of 150,000 initial conditions to let that evolve around. So, and there are new tools. How do we access tools going up and selecting a menu like this? And well, it gets tiring in 3 dimensions. That's one thing. You're not sitting at your desk kind of relaxed and moving your mouse around. When you're in a cave and you're interacting like this, it's very physical. So you don't want to have this older paradigm of interface. So we've come up with this kind of rotator tool, let you select things. But the punchline is this. So $500,000 single user system down to a $5,000 user system. This is all open source. It's DIY. We're putting together a website. You can do it yourself, and all the underlying software that Oliver and others of us have written, completely available to do this. It runs on these guys, all the way up to GeoWalls and other. But this is the near future. So in terms of input and control, I don't know if some of you might have seen the video, this little cigarette box sized thing called the Leap Motion, $70 USB device. You stick it down in front of your keyboard down here, and it has a series of infrared transceivers in here. It picks up and gives you this point cloud. So you can now forget that stupid wand thing or those Hydra Razor. It's going to be a natural interaction. You just get to touch your data. Oculus Rift. This replaces all of those heavy, giant displays, all the digital theater quality projectors in the cave. Forget it. $500. So called the Oculus Rift. They just closed their Kickstarter. I hope some people here were supporters of this. These are going to be available in December. Their SDKs will be available. So what does that mean? That means I will actually be able to demonstrate to you, rather than say it's an impossible story to make, I could just plug this stuff into this guy and have exactly the same immersive environment that I've been using in the cave or the Macroscope. So this is where it's going. The point here is in some ways not so much the different hardware instantiations. It's almost a mistake to focus on the hardware. The question is, what kind of user interface, what sort of tools should we be developing to help us understand all the data, all the computing that we're generating? And that to me is sort of a wide open thing. I take a little bit of encouragement from the fact that there is some of this sort of nonlinear theory that's telling us what these emergent patterns are and how to look at chaotic systems and measure that. So together, to me, that's the vision of this Macroscope, and it's coming soon to a desktop near you. Thanks.
Okay, thank you very much. Questions? Yes.
The last 3 or 4 slides were very interesting, but I was distracted by the rest of the talk, by the first part of the talk.
You're a gadget guy.
So no.
Oh, yeah.
So my questions are about the first part.
Right.
In one of your slides, you say, and you actually said, we want to build a meta theory,
right.
Theory about building theory.
Exactly. Good. Yeah.
That's the positivist program.
Yeah. Right.
Are you saying that we are going to be able to succeed in building a simple algorithm that will allow us to discover anything in any kinds of data set?
I would say through my study of these nonlinear chaotic systems and then the spatially extended pattern forming systems, those are domains in which I know how complicated the problem is. And using some of the mathematics that goes back to Poincaré and what other things developed in the 20th century, I'm very optimistic about doing that in those domains. I mean, I'm very cognizant of how complicated this is. The idea that it is a simple algorithm, I do not subscribe to that. But there is a way of thinking about how we build approximate models, and we use sort of a comparison across different models as they become more accurate to look at how smaller, less accurate models become larger, more accurate models. And thinking about that, I mean, I appeal to the vocabulary, I know, renormalization group, to look at how you go from imperfect assumptions, the world has finite correlations, to actually building up a model to describe infinite systems with infinite correlations. There is a way of doing that systematically. So I call that hierarchical machine reconstruction. So it's not just trying to build a model, but to look at, just be honest about the fact that maybe your initial assumptions are wrong, and look at how those assumptions are violated in a systematic way that can actually lead to ways of building more sophisticated models. I go from the cellular automaton 0-1 configurations to asking about these invariant sets, these domains. Oh, I find those, but then I factor those out of the system. Oh, they're particles. Oh, they're red and yellow particles. And then I try to describe those. And maybe there's some regularity with those things. People try to compute with these cellular automata. So there's a way of actually taking those particles and embedding a universal Turing machine at another level. So the point here, that really, if I'm saying this clearly enough, the point here is the process of discovery is one of changing your assumptions, of kind of moving up levels of abstraction. Must be some people who studied computation theory here. It's very much like an operator that moves you up and down the Chomsky hierarchy. finite state machines to push down automata, linear bounded automata, Turing machines, although it's much richer the way we're looking at it, many other intermediate steps. But that's the kind of idea of, so it's not a simple algorithm, it's kind of this hierarchical view.
Okay, Matthew, the last one.
So it was actually a semi-related question about the automated pattern discovery or relation discovery. What about things like symbolic regression, where there are well-tested methods for looking for partial differential equation solutions to and looking for constant expressions
Right.
So I was wondering whether you could just say something about that, or
There. Thank you. I wish you were a plant. So some time ago, you can take these notions from nonlinear dynamics, and there's a way of going from a single time series. You may not have all the probes into the system, but you could show you can go from a single time series to reconstructing a state space, either by taking successive time derivatives or time delays. That gives you an effective state space of the system. And then once you have the state space, you can think now of the states mapped in time into each other, and it then becomes actually a function fitting problem to get the differential equations out. So you can do this directly. And it's kind of been repopularized recently.
Yeah, so there's a technique. I know Shannon's not here, but there's a technique that guys at
I know, I'm
Eureka, yeah.
yes, it came out in Science, popularized in Wired magazine, but this is actually the original paper. And they actually got something wrong, so. But,
Yeah, I guess many other people may want to make questions, but time is now 40 minutes after 9, so
Okay, let's
I'd
move
like to thank James again, and please continue discussion. And then next keynote talk is ECR, a framework for interactive visualization.
I guess so. Okay.
Yes, by Curtis Wong.
Okay. This is going to be a much simpler talk than Jim's talk. It's almost kind of a here's what I did on my summer vacation talk. But I thought I would talk a little bit about, since the topic is generally about data visualization, to recap a little bit about what we've been doing with Worldwide Telescope. So Alex Ella yesterday talked about sort of 10 years of the work that he's been doing. And about 10 years ago, sort of when I got involved in this space, Jim Gray was giving this talk about databases meet astronomy, and this last slide was, if you're a viz person, we need you and we know it. And so I offered to help him. And then, we kind of got busy and built the first DR2 website. And then Alex suggested the following year that I go to this workshop in Chicago, basically with about the visualization of astrophysical data, and I was kind of intimidated because it's a room full of astrophysicists, not sort of unlike what we have here. And but he says, go ahead, tell him, give this little talk about what I had pitched to him, which was what I had said to Jim. I said, if we bring together all this astronomy data into one place, I think it's a terrific opportunity to create a learning environment for lots of people. Basically, not just having access to the images, but building a virtual environment. And then when you have this virtual environment, you can then connect those objects to other information on the web, and perhaps then in that environment build a virtual camera so that you can create guided tours in this space. He says, great, go build it. So this was sort of my original presentation deck that I gave there in Chicago, which was a very simple idea of bringing guided tours together into this virtual sky and connected to SkyServer. And then about a year later, I hired Jonathan Fay back there. And he quickly put together some work with the Sloan imagery from a tiled image browser that he had been working on for a few years. And we pulled that together and got sort of the green light to go build this crazy idea of the biggest telescope on the internet. And so that we launched about 18 months later at the TED conference with Roy talking about it. But since that time, I've been really wanting to sort of figure out how to connect that work with some more immediate needs of the growing data, and a lot of the public wanting to figure out how to visualize data. And so that's what what we started doing with the Worldwide Telescope. And about 2 years ago, how many people have seen the earthquake demo in Worldwide Telescope? Just a handful. Okay, so I'll show you this. This is a tour. We bring in about 40,000 is it behind this thing? It might be. Yeah, I think it's there. So I might want to turn the lights down here too. Okay. So when you're looking at the Ring of Fire, it's not particularly obvious sort of what's going on here. You know, why is this stuff happening in the middle of the ocean? We're used to thinking about earthquakes happening as a result of faults. But when you take the same data and you can look at it with perhaps a different underlying base layer, such as here, you start to see dark oceans and then light oceans, which I guess means shallower water and deeper water. And you start seeing, from the depth information, you're seeing a pattern here in terms of, oh, I get it. There's earthquakes are all forming along these subduction zones. And that same pattern is visible in lots of other places.
Can you show Washington, please?
Yeah, there's not as much going on here in Washington. As you can see, some things are somewhat below the surface. But if you go down in California, you can literally see the San Andreas. There we go. Let me move this. Okay, there's the Bay Area. And then as we move, you can sort of see the motion parallax really defining the path of where the San Andreas goes. This is the Blue Marble Earth image database, which is why it's sort of low res. And then when you come down here to Salton Sea, and there's a lot of activity here down by Baja. But the other thing about this is that, you know, by being able to visualize this stuff in 3D, is the ability to look at sort of data over time, which I think is something that it's not really easy to do today with commercial or even free tools, especially for the average person on the street. So we brought in some of these faults. You can see the Haiti earthquake there. But we're going to look at these earthquakes at about 1 million times real time. And you can really start to see large duration temporal structures, which are kind of interesting, as well as sort of exploring within these individual quakes themselves. So I'm going to go back to my talk here. So another example is, we're actually running kind of short on time. This is 500,000 data points, accumulated rainfall for precipitation in the United States. So these are constructed very simply, very much like a PowerPoint. If you're not familiar with how these tours are done, they're done like PowerPoint, where you're basically setting starting and ending points. And then the camera just goes and tweens between your different slides. You're just telling how long each slide is. But the nice thing about these things, even though they look like video, is that they're just paths in the environment. And so at any point you could sort of dive in and start to look at individual data points. Okay, let me put that one away. So this is, we started to get a little bit more grounded here, if you will. There's been a lot of interest in the product groups here at Microsoft in terms of visualization of business intelligence data. I took this public data from the city of Chicago, which is on narcotics arrest, and this is actually kind of interesting. We'll take a look here, and this is about 18 months of narcotics arrests. And you can sort of pick Anybody here from Chicago? Okay. Well, we're going to go into this in a little bit deeper. But you can sort of see the temporal pattern here of where the action is. And I'm going to... Can you overplot driving directions? Yeah, let me go and... Okay. So I'm going to take this data and we'll look at it, say, okay, so we can see all of it at once, and then start to look at this in terms of a count of domain values. So if you're looking here, let me sort this so you can see this a little bit better. So there's, of the 40,000 arrests, seems like cannabis is the drug of choice. So you can sort of see that about 52.3% of the arrests are for that. If you were looking at like, I think that's heroin. Heroin is kind of concentrated down in this area here. Crack, somewhat similar. Cocaine, as you'd expect, maybe is a different audience. In fact, if we go into this and look at, say, time, let's say date and hour of the day. So these, you see sort of a 9 to 5 here, and also a sort of a peak in the afternoon, which is kind of interesting. If we go and look at, let's go back to a different one. We were looking at heroin. Let's look at cocaine and do the same thing. Must be people working because they're kind of busy during the day and all the action happens after hours. But you know, the other things we can start to do is we can start to look at some of these by any other the columns that we have in the database, either looking at them by precinct or ward or any other sort of metadata that exists in there. And what we're using Worldwide Telescope for here is just to start to look at some of this faceted browsing in terms of the existing data that's there. Other things you can sort of do, let me put this away here. And this is not a final UI. This is just Jonathan and me sort of exploring what you could do here. Let me skip and go back here. So I want to sort of bring this back to the ECR reference that I made. When I first started with Worldwide Telescope, the information architecture was designed, in my perspective, around education. How do you get somebody interested in a topic that they may not already know something about? And to me, that was to start with stories. So we wanted the ability to quickly be able to engage somebody with a story, and that meant through this being able to create a virtual camera, to be able to put in narration and music and other kinds of things, animation, hyperlinks, that would all create an experience that was as good as a regular kind of documentary, but that because it was just a path in this environment, that it was fully interactive at any time, which allowed for individual self-discovery, and then connecting those objects to information on the web. So I think that same model, I think, also applies for how you might want to leverage doing data visualization, in that it's a way to share insight about outliers and other things in your data cloud, to be able to annotate them, to create this path of perspective about a particular insight and share those, especially when we're talking about bigger data and not being able to move the data around, but instead moving the analytics to the data itself. This might also be another methodology from which you can start to communicate and share insight. So I know there are already starting to be some places that are including GPUs in the cloud. Initially, I think for gaming, But the idea of trying to do something like this, where you're doing a camera in the space and I think Alex referenced this yesterday, of sending out an HD stream, if you will. But since it's rendered in real time like we do with our tours, it might be an interesting way to interactively explore some of these large data sets. And then, of course, linking any of those particular insights to other data sets that you can bring in as well. So some of the challenges that we're finding in working with making something like this usable by anybody is, of course, the initial challenges with dirty data, unstructured data. I think those are our biggest problems that we're facing. It's sort of a universal problem of anybody that has data, particularly around spreadsheets. And then sort of the next stages that we want to move to are source analytics in that space, applying machine learning. But that's just sort of understanding what happened as opposed to what really could happen. And that was a really important insight for me here. We want to bring in things like n-dimensional slicers and cubes to be able to segment data, not just along the existing metadata, but to be able to do the kinds of things across dimensions that don't already exist. Spatial queries as well, in combination with the things that we've shown. Complexity is always a problem in visualization, and we're trying to get to I think this, as we called it, working with the Office team about the shortest path to wow. And that's something we're spending a lot of time to try and make happen. Anyway, with the other work that we're doing in this space with another team related to us, which is the VX team, we're building a very large power wall. Right now it's 35 megapixels, but we're going to make it much bigger. The team is building a very different graphics rendering structure where we're trying to move computation closer to the pixels. So we're essentially sending functions and not pixels over the wire. We're bringing it together with some of the Connect technology, some speech and touch and multimodal and other sort of devices with it as well. That's a project called VX that's happening here. And sort of getting close to closing, this whole idea of integrated versus connected visualization applications. I mean, Worldwide Telescope was kind of an integrated application and has its own challenges because each one of these, of course, only do some of what you really need. And most of you doing astronomy stuff are probably using SAMP with a combination of other different components to be able to do the kind of visualization analysis that you're doing. And of course, it does require programming at various states. And that's something we want to try and avoid if we're going to make this available to generally everybody. Lastly, I want to sort of finish with this paper that Alyssa Goodman did. I was looking at it, and I thought I would share it. I have a copy of it on a thumb drive. Basically, it's a summary of the state of where visualization is if you're not up on there's sort of a past, present, and where she thinks the future is in terms of bringing different visualization technologies today for astronomy. And so I would highly recommend this paper as a summary, because yesterday someone had said, is there sort of an equivalent of a Tufte book? And while this isn't a Tufte book, it's certainly sort of here's a snapshot of where things are, and I think it was a good paper. So with that, I think we're back on schedule. Thank you. Well, I skipped a bunch of stuff deliberately. So.
Okay, we have plenty of time for questions.
One of your bullets was dirty data. I'm not sure exactly what you meant by that, but it seems to me there's an issue for all of these approaches to visualization and data wrangling, let's say. Mm-hmm. If there's observational noise in data and you have this powerful tool for viewing it in a whole bunch of different ways.
Theoretically, you could cull it out.
It's great, but it also gives you a bunch of statistical fluctuations. Okay, so in a way, that you're building a tool to generate false statistical fluctuations. So statistics comes in terms of countermeasures, but I think that's something that isn't often considered in building the tool. So do you have any tools that specifically are countermeasures to statistical fluctuations? That's my question.
Well, I think we haven't even gotten to doing as much statistics in this space yet, so not yet. I guess that's a simple answer. But we hope to. We hope to. Jeff?
In that context, the one thing when you read the old books on surveying is there's a difference between error and blunder. Okay, that error is something that you can understand what the structure of it is, and there's ways to beat it down with having lots of data. Blunders you have to detect. If you look at the history of shipboard observations of cloud cover, a significant number of them are on land, and it's because somebody wrote the latitude and longitude down wrong. And so that means that some of them on the ocean are also wrong, but not so obvious.
Right.
So like one way to detect that is to track an individual ship, and then to see if it jumps 1,000 kilometers one day. And so I think that's this idea of using something like this to be able to detect blunders in the data, where an instrument has just gone haywire, where a horse has stood on top of a snow pillow, kind of thing. It's very useful because the people who make real measurements out in the environment, we know all the things that can go wrong. No, we don't know all the things that go wrong, but data have a lot of glitches in them.
I mean, fortunately for you, the bad data that you've encompassed is very, very small, partly because over time you've come to recognize what's what.
That means, it's kind of, I know I've found lots of bad measurements. I also know I haven't found them all. All right.
Just to add something more to that. Some years ago, a graduate student of mine, we were working on a way of trying to represent this, and we used transparency as a way of measuring how, the errors on the data, basically. So something you're very certain about would be very optically thick, and something with high errors was optically thin. And then we used a hot gas model from the point of view of the viewer. So in fact, if you had a loss of poor quality data in one place, you would actually see it as being optically thick. So that's an approach maybe you could apply to that.
I've also been interested in possibly using sound, as a way to let you know of things that may not be visibly obvious, but are perhaps outside of some boundary. That it's amazing sort of how we can detect subtleties both in periodicity and amplitude and things like that.
So you had a haptic device, and data that you were very confident of was very firm. Data that was not so good was quite
kind of squishy. Huh?
Yeah, that's right. That's quite nice. But
that's a good analog.
Never cool on with astronomers. Astronomers are too conservative.
Yes. Are you considering putting a more abstract bottom layer than the Earth or the sky into the system?
Jonathan and I have been talking about that for a while. That's what I sort of meant by these sort of n-dimensional data slicers that we could use to do things with that would then be represented there or not. And people are always saying, hey, can you do the genome? That has its own sort of challenges, but at least it's sort of a linear sort of spatial model. Jonathan, you want to say anything about this?
Well, so as it sits right now, you can create some, empty reference frames that are just, multi-dimensional space and plot data in it and just use it without any concern to whether it's a coordinates reference system or anything like that, or any reality. Rob Fotland does a lot of demos where he has chemical, compositions of water coming out of a river, and he just creates a, three-dimensional grid of this right in the middle of the ocean where the river comes out. So it's sort of spatially located because it's associated with that river, but it's just a Cartesian grid, maybe with time, sitting out, in just some random spot to be able to use that as a little three-dimensional canvas to chart on. But you could do it against a background reference or without any other reference if you wanted. It's supported in the...
Yeah, we just don't have that black cube with nothing else in there yet.
No.
With a grid.
You just turn off all the background references.
Yeah, and then you have it.
So.
Okay. So have you ported this to an immersive environment?
That would be cool.
Yeah.
We haven't done it yet. It would be fun.
I mean,
we have...
Sorry, what do you mean we haven't done it yet?
Well, we have the big walls, but we...
we have it running in stereo walls, full dome planetariums, multi-channel, 80 megapixel planetariums. We have not done a full dome stereo, but there's actually, ourselves, but there's actually a guy in Germany who's using it for underwater, bathymetry and other things like that has a stereo under projected dome. So you kind of sit over this, and it's a inverted dome, and you can fly around in this. And he's trying to connect this up so that they can have two of them in different universities and collaborate with each other interactively on it. Another guy who's actually sold a Powerwall to Microsoft and asked me if I knew the person. It might be you that he was talking about. Not a one of the caves, yeah. But they're also experimenting with setting up worldwide telescope environments in that as well. So it supports that functionality. We don't have one. We don't have currently right now an immersive studio at Microsoft with it installed, but we have a lot of people in immersive environments like full dome and stereo systems that are using it that way.
Right. But the immersive means tracking, and it adds, like I said, it's impossible to make the point. You have to experience it to the extra level. I mean, one of our introductory demos is actually flying around the Earth and looking at the plate boundaries and where the epicenters are. You can just bring it right up and have the data right in front of your face, and you kind of look around like that, and in 30 seconds you know what tectonics is all about, as you've seen it.
Yeah.
Right here, when you're showing it to us, we're using the motion. And the brain is reconstructing it there. This way, it's all just completely done. And then the fact that you can, basically, you're controlling a program by your bodily position. There's something about that extra level of feedback that makes it so present.
I was in one at ExxonMobil, which does a lot of their exploration stuff, but I found their stuff, the latency was still an issue for me. Has it gotten better?
It's still a little bit tricky. Yeah, but there are some examples where it's really smooth, even for very complicated data.
Okay, that's one.
Actually, I have two questions. The first one is about did you think about other things of tools, interactive tools, for example, like the Microsoft Kinect, to interact with the visualized data? And the second question is about as it is accessible via the web, did you think to make it collaborative?
Two good questions. The Kinect, Jonathan has shown that I think 2 years ago. So it's done with the gesture part, and I think it's been improved a little bit. Speech is getting there. It's more of us focusing to spend more time on it. And then I think with regard to, what was the second question? It was about collaborative. Yeah, we haven't done the true collaborative where people can remotely control or communicate through it to give remote demos or anything yet. No.
I'll show you some of that.
Oh, okay.
In our our Eclipse release in December, we should have a collaborative environment that allow planetariums to connect with each other and drive along. And it's based on a multi-vendor protocol that we're going to be collaborating. We'll work from WWT to WWT, but it'll also work with Skyscan and UniView and some other things like that. We're in the process, because of the fact that there's several vendors involved and some people to try to drive that. it's not as fast as just getting it going, but that's the intention to do that. And the APIs that we already have, people have already built, like I mentioned, this underwater viewer, where you can actually build your own communication mechanism to synchronize across the web. But the fundamentals are already inside WWT. It's just we don't have a way of acting sort of like messenger in the cloud to connect people together, and that's sort of what is necessary to close the gap, because the network protocols for it are in place. It's just there's no sort of like game lobby, like they have in multiplayer games, and that's sort of necessary in order to make it easy for people to connect up.
Is that the first public announcement of that, Jonathan?
What's that?
Talking about the collaboration mode?
Of the collaboration?
Yeah, did you mention it at IPS?
That's where it came to life.
So, I've been working in Office for the past year and a half, so I've been a little bit removed from this. But anyway, thank you.
Okay, let's thank to Curtis again. And